Hello everyone. So this week what we're going to be learning is how to write functions. So I'm going to describe what you use functions for. There are a lot of details about how you implement functions and also how they work that I want to talk about. In addition to just talking about functions, I also want to talk about a specific kind of function called a recursive function. And this is something that students sometimes struggle with, so this will require I'm just going to be very forthright about this. This is going to require a lot of practice on your part in order to get the hang of this, but this is something that's extraordinarily useful in future courses where you learn how to implement data structures and complex algorithms, many of which require that you use recursion, at least for the simplest implementation. Okay, so we're going to talk about functions, how you make them, what the syntax looks like in Python, and some details about that. Then we'll talk about how they work, including introducing something called a calling stack. And finally, we'll talk about recursive functions, including how those work, and a specific kind of recursive function called tail recursive. So first, let's just talk about functions. Why do we create functions? Well, a function is really just a way for you to name a little snippet of the program. This snippet of the program can then be reused. So it's like a module that we can create. There's a couple different ways that we can create modules in Python. One way is that we could create a function, and another way is that we could create classes and objects, which we're going to talk about in a future lecture. Excuse me. So modularity is actually really important when you're developing programs because we humans have a difficult time understanding a really long, complex program because we can't understand all parts of it at any one time. So when you put things into a function, if the function just has 6 or 7 lines of code, it's very easy to understand the entire program, exactly what's happening, what the inputs look like, what kind of computations are happening in the function, and what is the output of the function going to be. If you create a whole bunch of these functions, you can then combine them together to make a more complex program, but you haven't really violated that small pieces guideline so that you can still understand how your program is working. There are actually a lot of other reasons why functions are very useful. The fact that they're named makes your program easier to understand, but also it's possible to actually test just the function. This is a special kind of function, functionality testing called unit testing, which we're going to address and actually implement a little bit later in this course. So a function is just a module of code. A function takes input, produces output, it has a name. So its inputs are called arguments, and its output is called its return value. Technically speaking, a function in Python can only have one return value, but because you could return a list or a tuple or a dictionary, then you could really return multiple values if you wanted to. So this is what a basic function looks like. On the right-hand side, I have some C++ functions just for comparison. If you happen to know an existing programming language like C# or Java or C++, then and even, in fact, JavaScript to some extent, you'll see some similarity between that and the C++ syntax shown here. But Python uses quite a different syntax. So remember that in Python, we usually use snake case. So you'll see that I use all lowercase here and an underscore in between the words of the function, whereas most other programming languages like C++, they use camel case where there's no underscore between the words and they capitalize the second and third and so on words. Also in C++, we specifically declare what kind of function it is, what kind of value is supposed to be returned by that function. What's the output supposed to look like? This one is a void function, which means it doesn't produce any output. But in Python, it's not mandatory that we declare what the output of the function is. So this one doesn't declare anything. And in the demo, I'm going to talk about how you can actually specify what the type of the function is. It's not in the main lecture, but we'll introduce it in the demo so as not to overload this thing. This lecture is pretty big, actually. Now, actually, this just sets aside the code. It just sort of puts it aside. It says, all right, in the name say hello from now on is going to consist of just this one line of code in this case. You can see that in the indent refers to the content of the function, just like it does with if statements and conditionals, and loops. nothing actually happens. Like, you don't actually execute any of the code in this function until you call the function. So to call the function in Python, you just use the name of the function and you use round brackets. And if there are any arguments to the function, you put them inside the round brackets. This one doesn't have any arguments, so you can see here the round brackets in the definition of the function. That's what the DEF keyword is short for. The definition of the function has no arguments, and therefore I can't pass any arguments. I don't need to pass any arguments to it when I call it. So this is a function that has no arguments, and it doesn't return any value. The only thing it does is print hello. Okay, so next we're going to talk about functions that do have a return value. So this function here doesn't have any arguments still, so you can see that the round brackets here are still empty. And when we call it, similarly, we don't put any arguments into the round brackets. But it does have the statement at the very bottom, return 42. So this is actually going to produce a value. The previous function didn't produce any value. And when we call this function, this is equivalent to the value 42 in this case, because it always returns 42. This is basically the same as saying answer equals 42. So this function doesn't do anything interesting yet, but I'm just demonstrating how you can return a value. So for example, if you make a function that we're calculating the sum of the numbers in a list, this is how you return the sum. So you could return a variable or an expression, or in this case, a constant value. Excuse me. Okay, so you can see that you can use it as part of an assignment statement. I could even use it in part of an expression. So for example, I could say answer equals 2 times get answer. That would work as well. You have to use these round brackets here because get answer is just the variable that points to the function. That's right, functions are actually variables too. So they're function type variables, and basically they contain the function code. So if I just use get answer without the round brackets, I'm saying the function, I want to put the function into the answer variable. But if I put the function name and then round brackets, I'm saying call the function or invoke the function. It means run the code that's in that function. And when it produces a value, take that value and put it into the answer variable. So that's basically how that works. So if you want to pass in some arguments, then what you do, again, you follow the snake case for the names of the arguments. We put them inside the round brackets. Now, Python doesn't require that you declare the types of these arguments, but you can, and I will show you that in the demo. And then at the end of this function, I just return age multiplied by 7. This is calculating the old idea that kids have about dog ages. Is a dog age is their human age times 7. And so to call this function, I just say get dog age, and I pass it inside the round brackets, the value that I want to be set to the age variable. So I want age to be equal to 24 in this case, and that's going to produce 24 times 7 as my result. And I could pass in different values and call the function again. So that's the whole idea of the function being reusable. Okay, and again, I've got some C++ equivalents over here if you're familiar with another programming language. If you're not, just feel free to ignore this stuff on the right-hand side. All right, so this is just showing you the basics. Overall, here's the basic idea. Use the def keyword, the name of the function, some round brackets, a list of arguments inside here separated by comma if you have more than one, with a colon at the end, just like you do for all things that have a block of code. And then you have an indented block of code that's going to execute. You can have as many lines of code as you want. It is a good idea to keep them relatively small. So if you have more than, say, 20 lines of code in your function, you might think about dividing it up into smaller functions. But usually, at least one return statement will be inside that function. Just a quick note of what return does. Return, in this case, produces the value of the function, but it also immediately exits the function. So if you have like a return statement, and then after that you have a print statement, that print statement is not going to happen, because the return statement exits the function before you get to the print. So you have to note that return actually means two things. It means, number one, stop executing the function, and number two, take this value and use that as the output for the function. If you have a function, it's usually customary to have some description of what the function does. Here's the Python way to do it. What you do is use a multi-line comment, or really a multi-line string. that works as a comment right inside, right below the first line of the function. So this is the exact same function, and here I have just a triple quoted string so that I can have it over multiple lines, and then it just describes what the function does. You can get into a bit more detail and describe all of the arguments, what the arguments are supposed to do, and so on, but this is actually a good start. There are tools out there that can read through these documents, these comments, and then actually produce like a web page API description compatible with the Python documentation. So you could do that as well for your organization if you're making a program that's quite complex and has lots of functions. You can generate this documentation. You can share it with all the employees in your company, and then those employees can look up what the function does if they don't remember what it's all about and what the arguments are supposed to be, etc. Can make it much easier for them to develop because it's very easy to forget what these things do if you've developed it yourself, and if somebody else developed it, you don't really have any other way of knowing what it is that the function does aside from the name of the function. And sometimes the description that the name gives isn't quite enough. So functions actually have a concept of a different kind of variable. So far what we've been seeing are just variables that are global scope. And that just means that those variables are accessible basically anywhere inside the program. They come into existence when you first give them a value, and they stay in existence all the way until the end of the program. We did a demo recently where we used the debugger, and I demonstrated that as we went through the whole program, the variable stayed there and it kept its value until the very end of the program. A local variable, so that's like its lifetime or its scope. A local variable has a different scope. A local variable only exists while this function is executing this one time. So if I call getAge and dog years, there's going to be a local variable called dog years factor that's created right here on this line when it runs the first time I execute the function. And then I return, and if you remember, the return statement immediately quits the execution of this function. And once that happens, the dog years factor variable goes away. It doesn't exist anymore. If we call the function again, it creates another new dog years factor variable, and again assigns it the value 7, but again it goes out of scope, or basically its life ends after the function finishes executing. And this sounds like a bad thing, but it's actually a very good thing. Because these variables only exist in the context of the function, it means that you're only going to use them in the function, and you don't have any like lingering values from a previous execution. You don't get a conflict with using the variable somewhere else in the program. It's only used here, and as a result, you're far less prone to error when you use local variables. So local variables are actually the most common type of variable that you'll typically use in a Python program. In fact, you don't need global variables at all. So in contrast to the local variables or the global variables, these are the ones that we've been using. So sometimes you can imagine that we have a function, and inside the function we have a variable called x. And then also outside the function we have a global variable called x. You can probably imagine how it's a little bit confusing which one you're trying to access. And so as a result, it's really, really discouraged for programmers to really use global variables at all, but especially using global variables inside the functions. So for my examples in the future, I'm mostly going to be using functions, and inside the functions, I'm going to be using global variables. We weren't able to do that up until this point because we didn't have access to local variables because they only exist inside functions. So we had to wait until we learned functions in order to do it. But it is generally a good practice to stick to local variables and avoid them. Now this slide is showing you how to break the rules. So just keep in mind that you're not really supposed to do this. This is declaring a global variable. And technically you don't need this line here where it says global dog years factor because we're actually reading the value. But what global does is it allows you also to write the value. Now I'm not in this function, but I just wanted this code here to show you that you could use this line global dog years factor, and now I could actually change the value of dog years factor. So for example, after that global line, I could say dog years factor equals 8, and now the global variable dog years factor would be equal to 8, not just during the execution of this function, but after the function's done executing as well. And that's another reason why we probably shouldn't use global variables. Functions shouldn't really have weird side effects like that. That's not recommended because that makes it very difficult to follow the trail of what's happening in the program. Programs should be as easy to understand, easy to trace as possible. So this is kind of goes against that, which is why we usually don't use global variables. Okay, so let's talk about how we actually call the functions. Okay, so here, for example, is a function. So it's another function. This one takes 2 arguments. So it's called random, and it has 2 arguments, low and high. And then there's some code inside to generate a random number. This is using a built-in function that does exactly the same thing as this function. And you can see there's a return statement, and this is the value that it returns. It's whatever this other random function returns is what it's going to return. And then when I actually call the function down here, I'm going to declare a variable called max. And I'm going to call my random function with 2 values. I'm just going to hard code the 0. That's the low value. And for the high value, I'm going to use the max value. Now, this is a little bit weird to people who are new to functions because it kind of seems like this 10 here has 2 names. It has the name max, because that's where we originally put the 10 into a variable called max. But then when I actually pass the 0 and max to random, it now has the value high. But here's the trick. In Python, because this is an integer variable, Python just makes a copy of it. So there are actually 2 separate variables. Max, which has the value of 10, that's a global variable in this example here. And then there's also the high variable, which is an argument. Arguments are local variables. And so this is only going to exist while the random function is executing. But it's also going to have the value 10, and that's why we call it pass by value, because what we're going to do is we're going to copy the value 10 from the max variable into the high variable. And this should be a little bit more obvious, but we also copy the 0 value into the low variable. Those are 2 local variables. Low contains the value 0, high contains the value 10, and they exist for this one line of code here. And then once this line of code is done, low and high no longer exist. They run out of scope. So that's something a little bit confusing at first, but just note that they are 2 different variables. Okay, one global variable max and one local variable high. Okay, so this is pass by value. And pass by value is actually really cool because it means a lot less confusion. It also means there are no potential side effects. If I pass the argument values in some other way, it's possible that the function might change the value of my variables. So imagine going back to this code here. Imagine if I couldn't see what random did, maybe random is going to change the value of this max variable. To me, that would be quite strange, and I wouldn't necessarily expect that function to do that. I kind of think of functions most of the time as being very mathematical function-like, in that they don't usually have side effects. They just compute a value based on the inputs, and the output is always the same if the inputs are always the same. So if it changed max, then that wouldn't necessarily be the case. So I wouldn't expect normally for it to have any changes to it. The way Python works, because max is being passed by value, it isn't possible for that value to be modified in any way. We can modify the value of high inside the random function, but that's a separate variable for max, so we can't actually change the value of max. So that's a big advantage, and it does mean that your program is a lot easier to trace. So that's why in Python, all really simple values would be all of the immutable types, and that would include things like numbers and strings. And immutable, we talked about how lists were mutable in the last section, and lists are immutable because we can add elements, we can remove elements, we can basically change the list, but we can't really change a string or change an integer. We can't really break it down into its component parts. We just can replace it effectively. We can replace an integer variable with a new integer, and we can replace a string variable with a new string. That's about it. So all of the immutable types are all passed by value. So things like strings and floats and ints and booleans, those are all passed by value. Okay, kind of looks like this. So here we have the calling code up here, which is where we declare a variable called age, and then we call the get age in dog years, passing age as an argument. And inside the function, we have another argument called human age. So it's a different name. I'm specifically using a different name so that we can contrast these two as 2 separate variables. and human age here is a copy of that. So it's got 21 in it still. They both have the value 21, but this one is a different variable. And then we multiply that one times 7. Okay, so that's appropriate in this case because I actually don't mean to modify age in any way. So pass by value is acceptable. The reason why we use it on immutable types is because immutable types are generally small. I guess a string could be very big, but ints and floats and booleans are all really small values, and so making a copy of it isn't such a big deal. For things that are typically larger, like lists rather, they're usually passed by reference in Python. So let's talk about pass by reference and how it's a little bit different. Okay, and there are actually a couple different variations of pass by reference. I'll talk about the one that's used by Python. But basically the way pass by reference works, a reference is sort of a pointer to where the original data is. So instead of making a duplicate copy, we do with pass by value, with pass by reference, the argument then becomes an alias for the original value. So this means, as a side effect, it actually is possible for you to modify the original value. So a function can modify the arguments that are passed into a function if it's passed by reference. That's true in all programming languages. C++ has a special ampersand operator that's used to differentiate between whether you want to pass by reference or pass by value, so you can pass anything by reference. In Python, that really isn't possible directly. You have to use various tricks in order to do it. But with Python, if you have a bigger type, I mentioned before a list or a dictionary, those will be passed by reference by default, and immutable types like int, float, boolean, those are all passed by value. Okay. So it is an advantage that you could theoretically have the function modify, but I will just say this is kind of the opposite because the other pass by value slides said that the advantage was that it doesn't modify. There are no side effects of the function. This allows you to have side effects. So I guess this could be considered an advantage or a disadvantage depending on your point of view. Obviously, it gives you the freedom to modify your arguments and therefore have your function have side effects. There are some situations where you might want that to happen, but also it's possible that you do it by accident. So you do have to take care to make sure that you don't do that. You realize that if you're changing an argument that was passed by reference, you're also changing the original data. So imagine, for example, a function that takes a list, and the list is supposed to be sorted. If you change the list that's being passed in, it's changing the original list. It's not making a copy of the list that's sorted. It's actually changing the list so that it is sorted. And depending on whether or not that's actually what you want or not, you may want to choose to write your code a little differently so that it doesn't modify the lists if you don't want it to. Okay, so there's a little picture of what that looks like. The calling code is over here. Here we have a function called remove first. And the definition of remove first is over here. It's calling our function from the last section, pop. And if you remember, pop 0 removes the first element. Index 0 is the first element. So pop takes an index of which to remove. And so I pass in lms by reference because it's a list. And therefore, when I call lms.pop0, it's actually going to change lms. But it's not just going to change lms because lms is really just a pointer back to the original numbers array, which was passed into the function when it was called. So we're also going to be removing the 1 from the numbers list as well. Okay, so that's important. With pass by reference, they are really two names. LMs and numbers are really two names for the same data. They represent the same data. It's in the same place in memory. So if I change the data using one of the variable names, it's also going to change the data for the other variables. That can be confusing because you can pass in a numbers that says 1, 2, 3, and then after you call a function, numbers has a completely different number of elements or whatever. That could be a little bit confusing, so do just take some care when you use pass by reference. And it's important to know that the bigger types like dictionaries and lists, they are passed by reference by default. Okay, now we've only so far been talking about passing in arguments in a positional way, but there's two different ways that we can pass in our arguments when we call the function. So here's the definition of a function. This one calculates the Euclidean distance, and this code is a little bit confusing, but basically what it says is subtract the two x values and square them, subtract the two y values and square them, and take the square root of the sum of those two squares. And that is the Euclidean distance. It's basically Pythagorean theorem. And so this returns the distance between the point x1, y1 on a grid and x2, y2 on a grid. And, I could call this function by using these arguments positionally. So x1 comes first. So if I pass a 0 as the first argument when I call the function, then presumably this 0 is the x1 value. And the next 0 must correspond to y1. But hopefully you can see that that might actually get a little bit confusing. So Python also allows you to pass these arguments by the names. So these are called keyword arguments. And in this case, I'm calling distance. I didn't have to change the function in any way. But when I called the function, all I have to do is say the name of the argument equals and then the value that I intend. So I happen to be calling this function with the arguments in the exact same order, but it's very clear that the x1 and y1 values are 0 and the x2, y2 values are 3 and 4. So it's a little bit more clear. It is more typing, yes, but it could maybe mean that you have less likelihood for error. So named arguments are pretty handy. As a nice side effect, we can change the order of these arguments and it won't have any impact. So for example, if I specified x2, y2 and then x1, y1, the function would still work the same way. So that's pretty handy. That's useful if you remember what the function does and generally what the arguments are, but you kind of forget what order the arguments are in. This can be helpful because you won't have to go back and look it up. So even though you have to type more, it might actually be better productivity-wise. Arguments can also have default values. So in this case, for instance, we've got a function, calculate interest, that takes 2 arguments. So we have an argument called principal, and we have an argument called interest rate. And I've given them default values. So the principal default value is 1,000, and interest rate's default value is 0.035. And all it does is take the principal and multiply it by the interest rate, so a really simple function. But I can call this function without any arguments because every argument that's in the argument list has a default value. You don't have to. You can supply default arguments for some and not default arguments for others. You do have to be careful to make sure that it's not like an ambiguous situation. If you're only supplying one argument, which one is it, right? So using positional arguments and using argument defaults can sometimes cause Python to be a little bit confused, especially considering we don't have to declare the types of these arguments, and I haven't declared the types here. And so Python's not even able to deduce which arguments which based on the type. But down here, if I'm using, you can see that I'm using named arguments down here because I only want to supply one of the arguments. To make it completely clear, I want to specify calculate interest with a different principal value and the default interest rate. So I'm still calculating 3.5% interest, but on a different principal amount. So that's how you can use argument defaults. And that's really useful in certain contexts where you don't normally need to supply an argument, but you can override it. So for example, if you're creating a graphics application, you want to have a border. The border by default could be black border, but you can override it with a blue border if you want to. So that way people don't have to provide a border color most of the time. They can just get a black border. But if they specifically want a blue border, then they have the option of doing it. So this provides the user of your function with the greatest flexibility. All right, so I want to talk about something that's kind of not directly related to functions, but then you're going to see why this is related after we talk about how functions work. So far, executing a single function and then having that function return its value hasn't been too complicated. But you will find in the near future that functions can call other functions and functions can even call themselves. And that can be a little bit confusing to understand exactly what's happening. You can understand your program if your program is working that way, if you don't understand how the functions are being executed by Python's interpreter or how they're implemented by the compiler in a different programming language. So in order to do that, we have to understand something called a calling stack. And a calling stack is a stack data structure. And we haven't encountered the stack data structure so far, but we are going to talk about the stack data structure in a later section. But I'm going to give you a preview of it right now so that it can be relevant for us when we talk about calling stacks. So the stack name is actually really important. You can imagine that you have a stack of items, like a stack of things like books, or maybe books isn't a really good example, a stack of really heavy things. So imagine a stack of cinder blocks. And imagine that you are exactly strong enough to carry one cinder block. You can't carry two. Okay, you're not strong enough to carry 2 cinder blocks. So you can carry 1, but you can't carry 2. So if we have a stack of blocks, if you think about it, if I want to put a block onto the stack, the only option I have is to place it on the top of the stack. Because if I wanted to put it, say, at the bottom of the stack, I'd have to lift all of those blocks up and put the other block underneath. I'd be lifting at least 2 blocks in order to do that, and that's not allowed. So in a stack, you can only put a new element on the top of the stack. You can't put an element in the bottom or the middle or whatever. And similarly, if you wanted to remove a block from the stack, you couldn't remove one from the bottom or from the middle because you'd have to lift up the other blocks to remove it. And that would involve you at least lifting 2 blocks at once, which you can't do. So you can only remove a block from a stack if you take it from the top. So you can only add a block to the top of a stack, and you can only remove a block from the top of the stack. Okay, so that makes a stack a very simple data structure. There's only 2 real operations that you can perform on a stack. Is putting something onto the stack, which means putting it on the top, and taking something off of the stack, which means taking it off of the top. Okay, so let's visualize that. So here I have an empty stack. Imagine this is just some concrete floor. And what we're going to do is we're going to implement a push operation. So imagine I'm pushing a new block onto the stack. And so push is the actual terminology that's used when we talk about stacks. So push literally means to insert a new element onto the top of the stack. Okay, so what I'm going to do is I'm going to push a block that says hello. So we put that at the bottom, of course. There's no other option, right? Everything has to go. The bottom of the stack and the top of the stack are the same. Like the stack was empty before. So now it's different though. There is a block already on the stack. So we can't put a new block underneath the hello block here. The only option that we have is to push the block onto the top of hello. So if I want to push a block that says class on it onto the stack, it has to go on top of hello like this. Now we're going to push another block that has 3 exclamation marks. The only option is to put it on top of class, because if I wanted to put it underneath class, say between class and hello, I'd have to lift up class, and I'd have to also still be holding the exclamation mark block. Put the exclamation mark block down, and then put the class block on top of it. That would require that I was holding 2 blocks, and I can't do that. I'm only strong enough to hold 1 block at a time. And similarly, I can't put it on the bottom underneath hello because I'd have to lift up the class and the hello block while still holding the exclamation mark block. That's 3 blocks at the same time. Put the exclamation mark block down, and then put the hello and class blocks on top. So I'm using that analogy to try to drive home that it's only possible to insert a new block on top of the stack, okay? Because that's the rule. That's how a stack works. All right, now we're going to do the opposite operation. So push is when you push a new element onto the top of the stack, and pop is when you remove an element from the top of the stack. And you may recognize the word pop from the pop function that's available in lists, where you can actually remove an element from a list using the pop function. And by default, if you don't pass any arguments to the pop function, it removes the element from the last position of the list. And that's not a coincidence. That's actually implemented by Python so that you can use a list as if it were a stack. So it's pretty handy. You don't have to implement your own stack. You can just use the built-in Python lists for that purpose. Okay. So pop, obviously, we can only lift off the top item. So I can't take class out of the stack right now because I'd have to lift up the exclamation mark and then take class. And I'd be holding both the exclamation mark block and the class block at the same time. I'm not strong enough to do that. I similarly can't remove the hello block because I'd have to hold the exclamation mark block and the class block and lift out the hello block, 3 at the same time, and I can't do that. But I can remove the exclamation mark block. So if I pop from this stack, the element that's going to pop is the exclamation mark block. Okay? And then if I pop again, the only element that I can remove is the class block at this point in time. And then if I pop again, the only element that I can remove is the hello block. So let's just make a quick note of that. Let's go through the animation real quick again. The way that I inserted the values was hello first, then class, then exclamation mark. And then when I took them off the stack, I did exclamation mark, class, and then hello. So notice the inherent reversal that was happening when I did the push and then the pop. The stack is really nice for reversing things. So if you want to reverse the order of a string, or you want to reverse the order of some list elements, a stack is a very useful data structure for doing that. All right. So the reason why we're learning about stacks, and that's just a basic introduction to a stack. We'll actually implement stacks in the future, in a future lecture. But for right now, I just want to note that in Python's interpreter, there already is a stack that keeps track of all the calling functions. So if we're in the middle of calling a function, there's something on the calling stack which represents the currently executing function. But not only that, but if we have a function that calls another function, we actually have something on the stack that represents both of those functions. So the thing on the top of the stack represents the function that's currently being executed, and the thing that's down below that is the function that called the current function. And in fact, we can have functions that call functions that call functions, and that would just be 3 elements on the stack and so on. We could have hundreds of elements on the calling stack if we want to. Okay, so the calling stack is a way for us to keep track of which functions are currently being executed. So imagine if I have a function that calls another function, the first function is going to pause until the second function finishes. The second function is going to take over, it's going to get some CPU time, it's going to do some calculations, and then we get to the return statement, that function quits, and we go back to the original function. But I have to remember exactly where I was. What was I computing at the time? What were the values of all of my variables? So that's the purpose of the calling stack. We have these stack frames, which are basically the blocks that represent the currently executing functions on the stack. And they contain 2 really important pieces of information. They contain all of the local variables and their values. That includes the arguments. So the arguments and local variables, those are all local variables. But also, where do I go back to after this function is executed? We call this the return address. Okay, we have to store the return address so that we go back to where we were when we called that function. So imagine I have a function called x, and that function x calls the function y. Well, when y is finished executing, I have to go back to where I called y in the x function, and so I have to have a return address, which is basically the location in memory where the instructions for the x function are that called y. So here we have a really simple function that is just one function. There's only 2 lines of code, and as you can see, the function's called b. It takes 1 argument, x. There also is a local variable being declared, y. So you can see lines 1, 2, and 3 are where the function gets declared. Line 4 is where we call the function and we take its return value, put it into a global variable, and then we print out the value of that global variable on line 5. So let's actually trace through this program. So the first thing that actually happens is we encounter the definition of the function. As I mentioned to you in the slides, this is really just a normal variable like any other. So it puts it into memory somewhere. In this case, just for simplicity, I put it at address 0. And that's just a variable, and the name of the variable is b. So it's relatively straightforward. But it doesn't execute any of that code. It just sets the code aside. So then when we get to line 4, it's ready to execute the code. So it knows it wants to execute the b function. You can see that we're passing the value 3 to it. So because of pass by value, we're going to copy that 3 into the x argument. So we're going to create a stack frame. So you see over on the right-hand side at the bottom, we created a stack frame. Now this is for our call to b. We are storing the return address so that we remember to come back to line 4 eventually. And now what we're going to do is we're going to create the local variables x and y. So on the first line of the function, we declare the argument variable x, which we know the value of because when we call the function with 3, it gets copied into the x variable. So we store x equals 3 in the stack frame. And then we also create a variable y set to 2 in the stack frame. Okay. Now, keep in mind, these are local variables. And once this function exits, we're going to get rid of the stack frame. It's not going to exist anymore, and the x and y variables go away. So that's a really important point for you to note about how functions get executed. That's going to help you later when we talk about more complex function calling. So now that we know the value of x and y, we can calculate the fact that x plus y is equal to 5. And so we return that 5. So that allows us to get rid of the stack frame. So the stack frame goes away. And we now say that the b's return value is 5. So we put that 5 into a variable called result. This is a global variable. And then finally, we can print that result. We should print 5. Here we have a more complex example where we have two functions, and one function, a, calls the other function, b. So let's see how that works. So you can see that from top to bottom, we declare the b function first and the a function second, but we're actually going to call the a function first. So first, the Python interpreter encounters the definition of b, so it puts that into memory as any normal variable. Then it encounters the definition of the a function, and it puts that into memory as well. And then when we get to the call on line 8, it knows that it's going to call the a function with the value 3, and the a function takes an argument. The argument's name is z, so we're going to use pass by value to copy the 3 into the z variable. So we're going to create a stack frame so that we can remember to come back here to line 8 once we're done with the a function. That's really important, and we also need to remember all the variables that we're currently calculating. Now, I haven't declared any variables aside from the functions a and b just yet, but generally speaking, we will, and we'll see that in this example when we call b from the a function. Okay, so we're going to create a stack frame that has the return address 8. Okay, and then we're going to go to the top where we're going to see the argument z is being declared. That's going to have the value 3, which we just passed in. Then on the next line, we declare a local variable called x, which is equal to 1. So we're going to also store that in our stack frame. Again, it's a local variable. And then when we get to the next line of code, you might think that we're going to create a local variable y, but we're not ready to do that yet, because when we have an assignment statement, we take the value on the right-hand side, we put it into a variable on the left-hand side, which may need to be created. But we don't know that value yet. So we have to wait until after b gets called. So what we're basically going to do is we're going to pause in the middle of the a function, and we're going to go and call the b function. And then once b is done, then we can continue the operation of the a function. This is one of the things that's a little bit confusing about the way functions work. But again, it's actually possible in the Visual Studio Code environment to step through the program and see how functions call each other. Like, what happens? What are all the variables? What does the stack look like? You can see that inside Visual Studio, and I strongly recommend that you do that. So what's going to happen is it's going to create another stack frame, this time for b. And b is going to remember where it needed to go back to. Now, when I return from b, I want to go back to line 6. When I return from a, I want to go back to line a. So I actually need a return address for every single function that's currently being executed. So for the a function, I create a separate stack frame with a different return address. Return address is 6. Okay, so then the little gray marker here is indicating these are places where I stopped, paused execution in order to execute some other function, and I'm eventually going to come back to these points at a later time. So when I get to the b function, you can see that I passed in the z value. If we look at the stack frame for the a function, you can see that the z variable has a value of 3. Since I'm passing this into b, I'm going to make a copy of it. This is passed by value in action. So we're going to create a variable called x, which also has the value 3. Okay. And you'll notice here that both functions actually have an x variable. And that's not a contradiction. It's perfectly all right for them to have the same local variables, and they don't conflict with one another whatsoever. Even though these two functions have x values with different values, the a function has an x value of 1, and the b function has an x value of 3. That's not a conflict, because currently right now we're executing the b function. So we only care about the x value for the b function, x equals 3. That x equals 1 is not visible to us right now. We only see what's on the top of the stack. Remember when I was visualizing the stack, I was saying it's like a bunch of concrete blocks. I only look at the top of the stack, I only add things to the top of the stack, and I only remove things from the top of the stack. So right now the top of the stack is the currently executing function, which is b. So that's where all the variables that I actually care about are. So then we declare a local variable y. That's another duplicate. There's also a y in the a function, but that doesn't matter. So that's going to be set to 2. And now that we know x and y, we can return the sum of those, which is 5. And now we can actually use the stack frame here to determine how to get back. It says the return address is 6, so we're going to go back to 6. And it also says the value of x and y are 3 and 2, so we can sum those and calculate the return value of 5. So then we go back to here, and at that, you can see that the stack frame has gone away because we're no longer executing B. So the top of the stack is now the A stack frame. And now we have everything we need in order to create that y local variable for the A function, because B of z is equal to 5. So we can create the y variable and set it equal to 5. So now that we know the value of x and y, we can compute the result of the A function, because the result of the A function is y minus x. Okay, so I'm going to use two things from the stack frame right now. I'm going to use the return address 8. That's where I'm going to go back to. But first, before I do that, I'm going to calculate y minus x, or 5 minus 1. So the return value for this function, this A function here, is going to be 4. So I'm going to go back to line 8, and I'm going to use 4 for the value of A3. Okay, notice that it's also going to clear the stack frame, because we're no longer executing the A function anymore. So now we create a new global variable equal to that 4 value that we just computed, and then we print it out to the console. So recursion. So functions aren't too complicated, and hopefully you'll find them a very useful tool, because it does allow you to make your program a lot simpler and easy, more understandable when you're reading through your program or somebody else's program. Recursion is actually something that can be used instead of iteration. So we talked about loops, for loops, and while loops before as one way to do things repeatedly. Another way to do things repeatedly is to use recursion. Recursion at first is a very complicated subject, and you probably won't believe me when you see the couple of examples that I have, but you'll eventually find that recursive solutions are often the easier solutions to certain problems, and then to think about it a little bit longer in order to figure out how you might do that in an iterative way, a way that uses loops. So that's something to keep in mind. At first, it is very normal for you to think, whoa, what? It's kind of mind-blowing and weird, and it doesn't seem quite right the way that recursion works. But if you practice it enough, especially with hands-on practice, not just reading through somebody else's code, but actually trying a program yourself, and especially using the debugger to trace how the program works, what the calling stack looks like, you'll eventually get the handle of it. But it does take a little while, so just keep that in mind. And my expectations are not too high. I'm not going to expect you to become a champion of recursion on the very first day, but practice with it and keep working at it. And eventually you'll find that when you take the data structures course in second year, or algorithms course, say in third year, you'll have the tools that you need in order to understand how to implement those data structures and algorithms. So that's a good idea. So what is recursion anyway? Well, a recursive definition is when you define something in terms of itself. And in fact, that's what a recursive function is as well. A function is a function that's defined in terms of itself. That means that the function calls itself. And that's a little bit bizarre, because basically what we're doing is we're calling a function that we're still in the middle of writing. And so that's a little bit strange. But if you trace it, you'll see that it actually makes perfect sense. So if you actually follow how this program works, it makes perfect sense. Now, this particular program right here has a fundamental flaw, and you might be able to guess it if you look at the name of the function. But it is possible to make recursive functions that don't have this flaw. I'm showing you this one at the beginning on purpose, because this is a function that's going to infinitely recurse. And that just means that if we call forever, it's going to print hello, and then it's going to call forever. Well, that call to forever is going to print hello and then call forever. And that call to forever is going to print hello and call forever, and so on and so forth. So hopefully you can see the idea of repetition that's happening. This will definitely repeat. It's definitely going to print hello again and again and again. But this particular one doesn't have any way to exit. So this is called infinite recursion, which is obviously something you don't want, because infinite recursion can only go on forever. So in this particular case, this is a very aptly named function. It's going to print hello forever. Now, actually, Python is pretty smart about this, and it creates a recursion depth that you can go. Every time we're calling a function, we're calling another function. And forever, the new forever is being called inside the old forever. And then again, on the next time, that new forever that we just called, it's being called in the other forever, which is still being called in the original forever. And so we end up having this depth of recursion that we're going into. And Python, I think, stops us at something like 200 or so. recursive calls as a way of saying, you probably don't mean to use this much recursion. That's a bit overboard. And it'll just stop you with a runtime error that says maximum recursion depth exceeded. So if you ever see that, and I'm going to show you that on purpose in the demo coming up, and I'll also, I'm going to demonstrate that for you momentarily, what it looks like on the calling stack. It's not what you want, okay? But I'm going to talk about how to have non-infinite recursion in a little bit. Okay, so this is an example of direct recursion. Direct recursion just means the function directly calls itself. It's not the only kind of recursion. It is the most common kind. Normally you have a function, it directly calls itself in order to solve the problem. But sometimes you'll have indirect recursion. So this is actually a picture of what direct recursion looks like. This is the function, and this is a call. You can see that the function calls itself. So a pretty simple diagram. Indirect recursion, there's a couple of examples here, is when one function calls another function, and that other function maybe calls the original. So here's an example where we have two functions. Forever2 calls forever1, and forever1 calls forever2. And it also prints hello, but you can see that it's going to go back and forth between forever1 and forever2, and forever1 and forever2. And that diagram kind of looks like this, where we've got forever1 and forever2. Forever1 calls forever2, and forever2 calls forever1. It just goes forever. It's still infinite recursion. We don't have any way for this to exit. It's even possible to have indirect recursion with 3 or 4 or 5 recursive functions. They're all kind of mutually recursive. Okay, so that's a possibility. Just keep in mind, it does happen sometimes. I don't think you'll ever see 3 or more. You'll often see either one recursive function, a direct recursion, or you'll have 2 indirect recursive functions. Okay. So now I want to show you a demo so that you can see how recursion actually works. What does the calling stack look like with a recursive call? Okay. So the example that I showed you first is an example of infinite recursion because there's no way to exit. We really need something like some kind of a conditional that says, are we done? So this code right here, it doesn't have any way to exit. So we have to have an exit condition. Sometimes we call that our base case in recursive speak. Okay, so when we're creating a recursive function, it's important to have a recursive step. That's how we repeat stuff. But it's just as important to have a base case. So we're going to have a base case and we're going to have a recursive case. Okay, so in this case, we've only got one of the two. So we're definitely calling forever within forever. So we've got the recursive case, but we don't have any base case, which is going to check, is the situation right for me to stop doing this? And there's no such thing in this code. So let's look at an example that does have an exit condition. So here's a function that actually does something kind of useful. So this is a function that actually prints the message a specific number of times, something that we could easily write a for loop to do. So it's not something I would specifically use recursion for, but we're going to start with the simplest examples at the very beginning. This example just says repeat n times. It takes 2 arguments. And the first argument is n, which is how many times I want to repeat. And the next one is what message do I want to print. So I want to print a certain message like hello world, and I want to print it n times, say 10 times, let's say. Okay, so you notice the very first line of this function is an if statement that says, all right, if n is less than 1, then I want to return. This is a special kind of return. You can see that it's not returning a value, it's just return. So remember before when I said the return function does 2 things. It quits the execution of the function, and it also provides the value that's supposed to be the output for the function. Well, this function is not supposed to produce any output at all. So it only does the first thing. It just basically quits the function. So it's important to note that if n is less than 1, this return will mean that I don't execute this other code. I don't execute the print, and I don't do the recursive call. That's really important because we're not stopping infinite recursion unless I stop that call to repeat n times again. Okay? So then we print the message, and then I call repeat n times. So it's definitely recursive. It's direct recursion because repeat n times calls repeat n times. It's the exact same function. But notice that the arguments are a little different here. I'm actually calling repeat n times with n minus 1. And since this is an integer, right? So this is being passed by value. What I'm actually passing in for the value of the new n value is the old n minus 1 value. So imagine if n initially is 10. When I do this recursive call, I'm going to pass in 9 this time. So now n has a value of 9 in this inner call to repeat n times. And then it's going to check to see if n is less than 1. It's still not going to be because it's 9. It's going to print the message, and then that repeat n times is going to call another repeat n times, the third one, which is going to be 9 minus 1 for the n value, or 8. And you can see, hopefully, that the n value is decreasing consistently. It's going down by 1 every time. So eventually it's going to be less than 1, which will cause us to return and not call the recursive function. So this eventually will finish. This is going to print hello 10 times. And so this is not infinite recursion. So let's contrast the infinite recursion with the finite recursion. So I have a variation of this version right here I'm going to show you a demo of, and I'm going to show you what that looks like on the calling stack. Okay. All right, in this example, we've got an example of infinite recursion. I put a little bit of different code in here so that the stack frame will be a little bit more interesting. And again, I'm going to leave out putting the definition of the function somewhere in memory. Know that that still happens, of course. Let's just start on line 5 so that we can see the first call. So we're calling infinite with the value of 1. You can see there's 1 argument. So we're going to store the return address of 5 in our first stack frame. And we're also going to copy that 1 into a local variable called x for the argument x. We're also going to declare another local variable y, which is always going to be 3. Then we're going to print the sum of those. So we're going to print 4, which doesn't have any representation on the screen. And then we're going to call infinite with x plus 1. So now x plus 1 gets copied in for the x value. So we're going to remember that we're going to come back to address 4 eventually. The x value is going to be x plus 1, which is 2 now. Again, we're going to create the y variable, which is going to have the same value, 3. And then we're going to print the sum of these two, which this time is going to be 5. Okay, then we call infinite with x plus 1. So now x should be equal to 3. Again, the return address is still 4 because that's where we made the recursive call. That's where I want to return to when we're done. Please note that this is tail recursion because the call to infinite is the very last thing to happen. But hopefully you can see that the value of x is going to keep going up. You can see on the bottom stack frame it was 1, on the second stack frame it's 2, and the third stack frame is 3, and so on and so forth. It's going to keep on going in this pattern. But there isn't any way for this code to exit. So you can see that we're just going to keep adding stack frames upon stack frames upon stack frames. And eventually we're either going to run out of memory, or in the case of Python, it's going to tell us that we reached our limit. We're not able to keep on going. So obviously I'm not showing you infinite steps, but in a programming language like C++, for instance, it will literally go until you completely run out of stack memory. Python will catch you long before then, but either way, it's not going to be functional. So it's not going to complete the operation anyway. So definitely watch out for infinite recursion in this situation. We have to have a base case. All right, in this example, you can see that we have a simple recursive function. This is a useful one because it computes the sum of a list, presumably a list of numbers. And if you look at the code, lines 1 through 5 are the actual definition of the recursive function. And you can see on line 4, I'm recursively calling this SUMList function. And on line 6 is where we have the call to SUMList with an actual list to be summed. So hopefully we can get the sum of 6 when we're finally finished. So as before, Python's going to read through this and declare a variable and put the code to the function somewhere in memory. I'm going to leave that out for the recursive demonstrations because now that you know that's how it works, there's nothing new about that. We're going to need a lot of space in order to visualize the stack frames for each of these calls to SUMList here. Okay, so we are going to start by executing the bottom line on line 6, and we're going to call SUMList with the value 1, 2, 3. Okay, so in doing that, we're going to create a new stack frame. So the stack frame is going to return to line 6 finally when we're finished, and it's going to have the LMs variable, which is initially going to be set to 1, 2, 3, which is what we passed in. We're going to check to see if that LMs is empty. In other words, the length of LMs is 0. It's not, so then we go on and make a recursive call of LMs 1 colon. Now 1 colon is the slice operator, and remember 1 is the index of the second element of the list. So this simply means that I'm going to drop the first element of the list when I call SUMList a second time. So I'm going to call SUMList. It's going to create another stack frame for the exact same function, but this is for a different call of that function. This one, it wants to return to line 4. So you'll notice that even the return addresses are different. It wants to come back to line 4 because that's where I currently am right now when I execute this SUMList function. And then you'll notice that it has its own LMs. So at the beginning, it's going to have just 2, 3 for LMs because we took the first element out. Then we're going to check to see if that LMs is empty. It's not. So guess what? We get to a recursive call again. So now what we're going to do is we're going to SUMList on LMs1 colon again. But now that LMs is different, that means I'm going to drop the first element again, which is going to set LMs equal to just 3, just the list that contains 3. So again, the return address is still 4 because we made this call in the same spot. LMs is going to be equal to just the list containing 3. We're going to check to see if that's empty. It still isn't. It still has 1 element. So we're going to recursively call a 4th time. So now when we grab the elements from index 1 onward, we're going to get an empty list. So LMs is actually going to be equal to the empty list now because we dropped the 3. And now we're going to check to see if the list is empty. It is now. And so we're going to return the value 0. And that's going to become the SUMREST value for our third call to this function. So we're going to create a local variable in the third stack frame that we can see, or the currently executing stack frame, which is equal to the sum of the rest of the elements of the list. So now all we need to do is we need to add the current element, the first element of the list, to that sum. So the sum of the rest of the list is 0. So all we need to do is add the 3 to it, basically, because the first element of LMs here is 3. Okay, and then we return that sum. So that's going to return SUMREST of 3. So now that SUMREST is 3, we're going to add that to the first element of LMs. First element of LMs is actually 2. Okay, so we're going to add the 2 to the 3, giving us a total SUMREST of 5. So we can return from that function. That gets rid of the stack frame, and it computes a SUMREST of 5, 2 plus 3. And then finally, we add the first element of LMs, which is now 1, to that 5, giving us 6. Okay, so then when we get back outside of all the calls to SUMList, we end up getting the result of 6 for total. And that just gets put into a global variable. Okay. All right. So let's look at some another example, maybe a more realistic example, because so far we haven't really seen any actually realistic examples. This is an example of a non-recursive function. If I want to implement a factorial function, then I would implement this. So it's called Factorial Loop, and I want to calculate n factorial. If you're not familiar with what factorial is, 5 factorial, for example, is 5 times 4 times 3 times 2 times 1. Okay, so basically whatever n is, we calculate n times n minus 1 times n minus 2 all the way down to 1. So that's pretty easy to do. We can use a simple for loop for that. The range function kind of takes care of most of it for us. Rather than calculate 5 times 4 times 3 times 2 times 1, I'm actually going up from 1 up to 5, or up to n in this case. But the result's still the same because the multiplication operation is commutative, meaning a times b and b times a are the same thing. So I can do that. Of course, I could actually pass different arguments to range so that it went down. I could go range n, comma 0, comma -1, for instance, and that would count down. That would work the same way, just kind of unnecessarily complex. And here I call a factorial loop with 5, and that's going to calculate 5 times 4 times 3 times 2 times 1, which I think is 120. To calculate this in a recursive way would actually be very straightforward because factorial, by its very definition, is a recursive operation. In fact, factorial is defined as the factorial of 1 is equal to 1, and the factorial of any other n, any other positive integer n, is equal to n times n factorial, n minus 1 factorial rather. And so factorial is defined in terms of factorial. And so that's a sensible way to define it so that we can have basically infinite, right? I mean, if it's possible for me to know what 800,000 factorial would look like, I mean, I wouldn't be able to calculate that big of a number, but I do understand that 800,000 factorial would be 800,000 times 799,999 times 799,998, and so on all the way down to 1. So conceptually, it's pretty easy to figure out what factorial means based on a really, really simple but recursive definition. I could write a recursive function to implement this very simply. In fact, I could do this in just 3 lines of code. So I think what I'm going to do is I'm going to leave this as an exercise for you, and then we'll cover this in the demo part of this section. Okay, so try to use the definition of factorial, which is basically 1 factorial is equal to 1, and n factorial is equal to n times n minus 1 factorial. Use that concept somehow to figure out how to create a recursive definition of factorial. Okay, so then I'll come back to that in the demo part. All right, so one special kind of recursion that I want to address real quick is tail recursion. And tail recursion is when the very last thing to happen in the recursive function is the recursive call itself. So the reason why this is worth mentioning is that oftentimes it's very easy to convert a tail recursive function into a for loop or a while loop without a whole lot of thought. And so it can become almost an automatic process. And in fact, it can be an automatic process. The compiler or the Python interpreter could even convert a function that's tail recursive into a loop. And so here's an example of a tail recursive function. Remember, tail usually means the back of things in computer science. So here's a function. This is a function that I've actually already shown you, but the last line of the function is the recursive call. There are no other recursive calls anywhere else in the function. It's only the last thing. And not only that, but it's the last thing to happen. And so imagine if I was doing something like print n times, times 2, if it returned a number or something, then I wouldn't be able to do the times 2 until I figured out the value for print n times, which means that the multiplication is the last thing I do, not the recursive call. I'd call the recursive call first and then multiply it by 2. So that's not really what I want. In this case, this is the very last thing to happen. The last thing that happens is I call print n times recursively. So this is an example of a tail recursive function. And this should be very easy to convert into a for loop. And if I'm not able to convert it to a for loop, it's probably possible that the compiler or the Python interpreter is able to make it more efficient anyway. And you may have noticed that when you call functions, you create these stack frames, and the stack frames take up memory. And if I'm doing an operation that requires a lot of repeating, that's probably a lot of recursive calls. Every one of those recursive calls takes up some memory. Now, sometimes you can avoid using that memory, even if you don't use recursion. So sometimes you might need to still allocate some memory to use in order to solve whatever problem you're trying to solve if you don't use recursion. But there are a lot of recursive functions that use memory that don't require using memory when you have the iterative version of that same problem, that same solution. And so oftentimes what people do is they use a recursive solution first just to kind of get the idea going, and then they'll spend some time converting that into an iterative version. Well, tail recursive functions are actually really easy to convert to a loop. So that's one thing to note. Okay, so here, for example, is our print n times function. And to convert that into a loop, well, it's kind of easy because I can see that we start at n, and we go down by 1 every time. Like the message doesn't seem to change. But we start at n, we go down by 1, and we quit when we get to n equals 0. And so basically I can see that I'm repeating for n, I'm repeating for n minus 1, I'm repeating all the way until, but not including 0, right? So the total number of repetitions is n. And so I can turn that into a for loop here. This one's probably not the most accurate equivalent here, but this is equivalent because I'm doing range n. And so range n should happen n times, the same number of times that the recursive function does. Now, there are different I values in this case, or n values over here, because these start out, like say I'm calling print n times 5. It's going to be 5, 4, 3, 2, 1. And these I values over here are going to be 0, 1, 2, 3, 4. So they're different values, but that doesn't really matter because the only thing I'm doing in a repeated way is print message, which doesn't use n or I. But if I really wanted the values to be the same, I could just adjust the parameters of range. For example, I could say from range from n down to 0, step size -1, and then that would use the same values for I that exist for n over here in the recursive version. So I can make it as close as I want to. It's relatively easy to do this conversion. Okay? And one of the keys of tail recursion is that it's possible, like the calling stack is really kind of unnecessary. With a non-tail recursive function, everything on the calling stack, we need it because the calling stack allows us to go back there later. So we need the return address so that we know where to go back. But when we do go back, we also need all the variables that we were in the middle of working on so that we can go back to our calculations and finish the calculation. So we need all of those local variables and we need all of those return addresses. One return address for every function that we're returning from. With tail recursion, because the recursive step is the very, very last step, then this is actually not that important because we don't ever really need to go back to that function. The last step was the recursive call, and we're doing that right now. So when the recursive call is done, we actually don't need to go back. And so it's much easier to implement tail recursion because really the calling stack becomes mostly unnecessary. All the stuff on the calling stack is not needed. That just means even though a tail recursive function being implemented as a loop isn't particularly faster, it will take up less memory because we don't need all of those stack frames. Okay, so it can help us. One measure of performance is how much memory it uses. So it can help us in that way. Okay, so quick, just to make sure everybody understands tail recursion, I want to find out if you know if this function is tail recursive. So let's think about it for a quick second. I want to give you a guess. Say your guess out loud. Even if you're sitting home alone, you can blame it on me. You know, nobody's gonna think you're weird for talking to yourself. I asked you to do it. It's really important, and the reason is I want you to commit. Because actually, if you're wrong, I kind of hope you're wrong. This is no outcome going to affect your mark here. I kind of hope you're wrong because actually it means that you'll remember something more likely if you guess the wrong answer right now. So don't be afraid to guess the wrong answer. Remember that failure is fantastic. The road to success is paved with failure. So you really want to fail early and often. If you fail early and often, that means you're failing before it's exam time. You're getting the hang of it. By the time tests come around, you're gonna be doing it right. So do it wrong first on purpose, or don't be afraid to do it on accident, so that you can know exactly what's going on when you're ready to do it the right way. Okay, so the answer is this is not a tail recursive function. Now, I could understand if you were believing that this was tail recursive because, like, literally the last thing in the function, like the last characters of the function, are to call Fibonacci with n-2. If you're not familiar with the Fibonacci sequence is the sequence 0 and 1, the numbers 0 and 1, and then the numbers after that are the sum of the previous two. So the next one is 0 plus 1, which is 1. And the next one is 1 plus 1, which is 2. And the next one is 1 plus 2, which is 3, and so on. And so if we want to calculate Fibonacci, this is kind of the most obvious implementation of Fibonacci because it literally says, well, the first two numbers, like 0 and 1, are just either 0 or 1, right? They're just whatever the n value is. And if it's bigger than 1, then we just add the previous Fibonacci number to the one before that. And so this is really straightforward because if you look at the mathematical definition of Fibonacci, it's the same as this code. It's just this is written in Python syntax, but otherwise it's basically the same. But remember what I said, tail recursion happens when the last thing to happen. I don't mean last as far as characters go. I mean chronologically last. What's the last thing that's going to happen temporally in this function? And what's really going to happen is it's going to calculate Fibonacci of n-1. Then it's going to calculate Fibonacci of n-2 because you need both those values before we can add them together. So we can't do the add until we have both the result of Fibonacci n-1 and the result of Fibonacci n-2. So the addition is the last thing to happen in this function, not recursion. So it's not tail recursive. And another reason why it's not tail recursive is even though one of these things is at the end, The other one is not. You have to, like, the only recursion is the very last step in the function. So this is not an example of a tail recursive function. It's a function, and it's definitely recursive, and it's correct, by the way. We will find out later that this is horrible performance-wise. When we get into algorithms, we'll learn a little bit about that. So we'll learn a little bit about how to analyze algorithms. But for now, anyway, this is an implementation. It's relatively straightforward. Okay, so now what I'm going to do is I'm going to show you a quick demo that demonstrates how tail recursive functions operate and show you the calling stack. And then I'll proceed to demonstrate how the calling stack can be cleaned up and optimized so that effectively you're running something that's similar to a loop in the end. Okay, so that's basically it. So you're going to find that functions are probably the most important thing that you've learned about structuring your program, because a function is a named thing, it automatically adds some readability to your program. Because when you call your function, you're calling something that has a name chosen by you. So you should know what it does if you choose a name that actually makes sense, it describes what it is the function is supposed to be doing, then you don't need to worry about how that function is working. You can just read the name of the function and say, oh, I know what this is doing. So that can really help the readability of your program. Plus, it breaks it up into smaller pieces, and we talked about how that's really useful because you can understand really small pieces individually, and then you can just trust that the function works without dealing with, what does it look like inside that function. I can just trust that it works based on the name being something sensible. You can also test the function on its own because it's a relatively small unit. I can actually test it out, give it different arguments, and make sure that the outputs for the function are exactly what I expect them to be. That's called unit testing, and we're going to put that into practice a little bit later. So functions can actually be recursive. We talked about that. There's tail recursive and non-tail recursive functions. And, recursive functions can also be direct or indirect. But recursive functions are a particularly important thing for you to learn right now because I'm giving you basically a year to learn something that probably will take you a few weeks or maybe even a month to learn. But if you don't put the time into it, it's always going to be something baffling to you. You're never going to truly understand it. But everybody who puts in the time will definitely understand it eventually. So my recommendation is just jump right into it. Try out some recursive functions, try to solve some recursive functions, download some of my recursive functions, try them out in the Visual Studio Code environment, use the debugger, trace them, look what the calling stack looks like. You can learn so much from that whole process. Okay? Anyway, that's enough for now. So thanks everybody, and I'll see you next time. In this example, we have a function that is tail recursive. So I've taken that sum list function and I've just modified it ever so slightly so that it has a second argument, base, which has a default value of 0, and that makes it convenient for me because I could still call the sum list function in the same way, the sum list tail function in the same way that I called the sum list function. But the base is going to be our running total. We're just going to pass it down into the recursive calls. So I'm going to sum the values one at a time, starting at the beginning and working my way toward the back. And each recursive call is going to deal with the sum of the remaining part of the list, excluding the first element of the list. And so it hasn't really changed that much. But let's take a look what the calling stack looks like as a result of this small change. So again, I'm not going to show you where the function code goes in memory. Just know that it's put somewhere in memory. So in this case, we're going to call sumListTail with 1, 2, 3 again, just like we did last time. The return address is going to be 5 because that's where we made this call. And we're going to copy in the elms, and it's going to be equal to 1, 2, 3. And of course, base is going to be equal to 0 because that's its initial value. And we didn't pass in a value, so we're going to use the initial value. We're going to then check to see if elms is empty, and it's not. If that were the case, we would return base, but we're not done yet, so we can't do that. So we're going to make a recursive call. Again, just like before, we're only going to take the elements other than the first element. But now what we're going to do is we're going to take the old base, which currently is 0. We're going to add to it the value of the first element of the list. So now we're going to have a different base value being passed in. So you can see the return address is 4. That's where we're currently making this call. Elms is going to be equal to 2, 3. And base is going to be equal to 1, which is the value of the first element of the list. We're going to check to see if elms is empty. It isn't. So we're going to need another recursive call in order to complete this operation. But let's take a quick look here. we're going to call SumListTail with LMs 1 colon. That means the remaining elements skipping the first elements. We're going to skip the 2 this time. And just the first argument LMs is therefore going to be just the list containing 3. But then we're going to take base, which is equal to 1, and we're going to add to it the first element of LMs, which is 2. So we're going to, this time base is going to be equal to 3. Okay, so we're going to remember that the return address is 4. The LMs value is going to be the list containing just 3, and base is going to be 3. All right, now we're going to check to see if LMs is empty. It's still not empty. So we need one more recursive call. So now let's take a look. LMs 1 colon is going to remove the first element from the list, which means that LMs is going to be an empty list. And now base is going to be the old base, 3, plus the value that's in the list at the first position, which is 3. So 3 plus 3, that's going to give us our 6. And so we're going to have return address 4, LMs equals empty list, and base equals 6. Now we're going to check to see if LMs is empty, and this time it is. So we just return the base value, or 6. So that 6 is actually what gets returned as the value of SumListTail. So now we're going to back out of that first call, and so now you'll notice that the return value for SumListTail is the last thing that's happening in this function. We're just literally taking that value that we just computed, and we're just returning it. So we don't have to do any new calculations. So we don't really need any of the local variables in this function. We can just literally just, whatever value we just received from the recursive call, we're going to return it as our value, unchanged. So that's literally the last thing that this function does. So we can exit out of that function. And the return value of that function, which is still the 6, is going to now be the return value for the current execution of SumListTail. So we're going to exit out of that one. And then finally, when we get to the last one, this is the original call that was made to it. And this was made on line 5. So when we return this value, this is going to return the exact same value again, which is again going to be that same 6 value that was returned by the recursive call to SumListTail. And that 6 value is going to be passed to the, added to the total variable here. So the total variable, we're going to clear out the stack frame, and we're going to generate the total variable. Okay, just going to go quickly back so that we can take a look at the stack now. So let's look at the stack when it was fully built. So here we are. If we look at the very end of the function where we call SumListTail, we're not doing any computation at this point, and we technically do need to know how to go back. We need to know the return address to go to line 4, but kind of we also don't, because all we're doing is we're going back to that line 4 just to quit that function. So when we quit the inner call to SumListTail, we go back to line 4 and then quit that one without doing anything new. So we don't need the local variables, LMs or base, and we really don't need the return address either. So all of the stuff on the stack, all 3 of the top stack frames here, are completely useless. We don't need that information anymore by the time we get to this final call. So that's one of the important things that I wanted to note. So really, the only thing that we need on the stack is just this information. And if we wanted to, we could adjust the LMs and base variables here if we wanted to in place, in memory, in the stack frame, so that we're keeping track of how everything works. Anyway, so I'll show you how that works in the next demo. All right, here we are with the final tail recursion example. This is the exact same code, so the code hasn't changed at all. I just want to show you how the Python interpreter or a compiler might optimize the calling stack to make this execute more efficiently. And by more efficiently, I mean it would use a little bit less memory. So let's try to see how that works. Okay, so first thing we're going to do is do the outer call with SumListTail of 1, 2, 3. So we're going to create a stack frame, of course, for that, because we are calling a function. We need a stack frame. We need to know how to get back here. We need to know that line 5 is where we originally came from. So we're going to create a stack frame. And of course, we're going to create the local variables, LMs and base. So we're going to declare those. And of course, LMs is going to be 1, 2, 3, and base is going to be 0. It's the default value. But now from here on out, for the rest of the execution of this function, all we're going to do is we're going to update LMs. when we make a new function call. And the reason I can do that is because I don't need the old value for LMs anymore. Let's actually watch this step through. So we're going to check to see if it's empty. It's not. So we make a recursive call. The new value of LMs is going to be 2, 3. Well, the old value of LMs, 1, 2, 3, I actually don't need that anymore because I'm putting the 1's value into the sum when I pass the new base value. The new base value is going to be equal to the old base value of 0 plus the first element of the list, 1. So I don't need the first element of the list anymore. I also don't need the old value for base anymore. The new value for base, 1, is actually the value I care about now. So I don't need that. I can actually just adjust LMs and base in place. That's just going to modify those values. So we'll see those change to 2, 3, and 1 here. And then we check to see if LMs is empty, and it's not. So we're going to make a recursive call. And then I'm just going to remove the first element from LMs and adjust the base to be 1 plus 2, or 3. So LMs is just the list containing 3, and base is just 3. And then we check to see if it's empty. It's still not, so we need one more recursive call, but there are no new stack frames, so it doesn't really use up more memory. So now we get rid of the first element of LMs. We update base to be 3 plus 3. And now LMs is finally empty, so we can return the base value. It's still 6, it's still the exact same value, but we saved a lot of memory in the process, so we didn't need to create stack frames for every recursive call. Python was smart enough to recognize because it's tail recursion, we don't need all of those stack frames. The stack frames are actually completely unnecessary.